Lenz's law states a changing magnetic field through a closed conducting loop induces a current. The induced current has a direction such that the magnetic field that it generates opposes the change in the magnetic flux. The first thing we want to do in working with problems involving Lenz's law is to determine the direction of the applied magnetic field that passes through a conducting loop. The direction of the applied magnetic field is important because in knowing that direction, that'll allow us to determine how the magnetic flux is changing. Is the magnetic flux increasing through the loop? Is it decreasing? Or is it staying the same? Depending on our answer to this question, we'll need to be able to determine the direction of an induced magnetic field that will oppose the change in the flux. And finally, we'll determine the direction of the induced current. To do that, we'll use the right-hand rule to determine the current direction in the loop that generates the induced magnetic field. So let's apply these tactics to the following example. Suppose that we have a square loop of copper wire that is pulled through a region of uniform magnetic field at constant speed. Let's determine the direction of the induced current in the loop. We have four situations, A, B, C, and D. Let's rank each of those currents in order from largest magnitude to smallest magnitude. So let's begin our analysis with the first loop that is outside of the uniform magnetic field. Notice the magnetic field is indicated with a series of dots. That means that the magnetic field is pointing straight towards us out of the screen. The current loop is about to enter the magnetic field, but it's still outside of the magnetic field. So in following our tactics, step one was to determine the direction of the applied magnetic field that passes through the loop. Well, zero magnetic field passes through the loop. With that said, we have to determine how the magnetic flux is changing. Well, in order to look at magnetic flux, let's start off by writing the equation of magnetic flux when we have a magnetic field that is uniform over an area. That magnetic flux equation is given as the dot product of the magnetic field and the surface area vector. For this magnetic flux to change, we would apply the time derivative to the dot product between the magnetic field and the surface area vector. When we evaluate this dot product, we see that the change of magnetic flux is given by the product rule of the magnetic field dotted with the time rate of change of the area, plus the area dotted with the time rate of change of the magnetic field. So here is our expression for the time rate of change of the magnetic flux. For this problem, there is no magnetic field passing through the loop right now. The loop is well outside of the magnetic field, so the rate of change of the magnetic field with respect to time is 0. Now, what about the area? Well, the effective area of the loop that's exposed to the magnetic field is 0 as well, because none of the magnetic field is passing through the loop. So what this means for this first part of the problem is that the time rate of change of the magnetic flux is equal to 0. So in other words, if there is no change in the magnetic flux, there can be no induced current. So for this problem, the induced current is equal to 0. Now, put more simply, and looking at this more conceptually, there is no magnetic field through the loop, which means there is no change of magnetic flux for the loop, which means that no current can be induced. For part B, the loop just enters the magnetic field. Well, we could look at this in a couple of different ways. One way of looking at it is, since the loop is entering the magnetic field, just that fact causes a change of magnetic flux. Lenz's law says that there will be an induced magnetic field whenever there is a change of magnetic flux in order to oppose the change of magnetic flux. Here we have a conducting loop that is entering a magnetic field, so the magnetic flux is increasing. Since the magnetic flux is increasing, the change of magnetic flux will induce a current in the loop that will create a magnetic field to oppose the change of magnetic flux. Now we can see that formulaically by just working out this time derivative of magnetic flux. Remember, the time derivative of magnetic flux is given as the time derivative of the dot product of the magnetic field and the surface area vector, which is just the dot product of the magnetic field with the time rate of change of the surface area vector plus the surface area vector dotted with the time rate of change of the magnetic field. Now for this problem, the magnetic field is not changing in time. So we could say this quantity is equal to 0. But what is happening is that the surface area vector is changing in time. So what does that mean by the area vector is changing in time? Because you're looking at this and you're looking at it and you're saying, well, the loop isn't changing its area. And you're right, the loop isn't changing its area. But remember, magnetic flux doesn't have to apply to a physical loop in space. It can apply to a mathematical area in space. And if you look at this, let's look at the effective area right now in which the magnetic flux is changing. So this dotted line and this shading represents the effective area of the loop that is exposed to that magnetic field. And as this loop continues to enter the magnetic field, that effective area increases. So that means there is a time rate of change of the area. Since there is a time rate of change of the area, we could say that the rate of change of the magnetic flux is given as the dot product of the magnetic field with the time rate of change of the area. And since this quantity is not equal to 0, that must mean that there is a current induced in the conducting loop to oppose the change in the magnetic flux. That current will create its own magnetic field to oppose the change. We need to know the direction of this induced magnetic field in order to determine the direction of the induced current in the loop. So how do we figure out the direction of this induced magnetic field? Let's look at how the magnetic field is changing in number as the loop enters the magnetic field. So notice right now in our diagram, in the shaded region, we have two magnetic field lines coming towards us. And you can imagine that as the loop moves to the right through the magnetic field, more and more magnetic field lines will enter the loop. Remember, magnetic flux is directly proportional to the number of magnetic field lines crossing an area. Well, if the number of magnetic field lines crossing this area is increasing, Lenz's law states that a current will be produced that induces a magnetic field to oppose that change. What that means is a magnetic field will be induced to go against the increase of the magnetic field lines going through that loop. I'll indicate that with these two X's here. These two X's represent the induced magnetic field, and notice how I have it going away in the opposite direction of the magnetic field lines crossing the loop. I have it going in the opposite direction because if the number of magnetic field lines are increasing, thereby increasing the magnetic flux, a current is induced to produce a magnetic field to try to oppose that. It makes sense that the magnetic field induced by the current would be opposite in the direction to the magnetic field passing through the current loop. The reason why that makes sense because if you look at the magnetic field lines from a different perspective, here is looking at it from the plane of our loop. This vector going up is the magnetic field going through the loop. This vector going down is the magnetic field that's induced. They are in opposite directions. And what that means, since they're in opposite directions, those two magnetic fields will create an interactive force. When magnetic field lines are in opposite directions, that indicates a repulsive magnetic force between them. That repulsive magnetic force is going to try to prevent the current loop from going any further into the uniform magnetic field. So it'll be a force that will slow down the loop and try and prevent it from going any further. Now, if we want to determine the direction of the current that induces this induced magnetic field, which I will label in this diagram that I just drew, be induced, and this is the original magnetic field passing through the loop. To determine the direction of the induced current, we'll use the right-hand rule and the version of the right-hand rule that says put our thumb in the direction of the magnetic field. So here's the thumb of our right hand. I'm putting that in the direction of the magnetic field. And then what we do is we curl our fingers, and the direction our fingers curl is the direction of the induced current. So that's my poor attempt at drawing my right hand and my thumb. My thumb is in the direction of the magnetic field that's been induced. The fingers of my right hand is curling around. And if we were to look at this from above, we would see that this would represent a clockwise induced current. So the current in this conducting loop is circulating around in the clockwise direction. So we will say I of B is clockwise. For part C, notice that our loop is completely inside the magnetic field. Since the magnetic field is uniform, there is zero change of magnetic flux. The number of magnetic field lines is remaining constant as this loop passes through the magnetic field. As long as it's completely in the magnetic field, the number of magnetic field lines remains constant. Because the number of magnetic field lines passing through the loop remains constant, the magnetic flux, or rather, the rate of change of the magnetic flux is equal to 0. Since the rate of change of the magnetic flux is equal to 0, there can be no induced current. So the induced current for this one is equal to 0. And finally, when the loop tries to leave the magnetic field, well, there is going to be a change of magnetic flux as the loop is leaving the magnetic field. And similar to what we did for part B, this change of magnetic flux can be visualized mathematically as being the dot product between the magnetic field and the time rate of change of area. Now, we don't have to be that mathematical on this. All we have to really do is look at how the magnetic flux is changing. So if this is our effective area, notice how the magnetic flux is decreasing. What that means is, as the loop is leaving the field, fewer and fewer magnetic field lines are passing through the loop. The universe does not want this change. It wants to keep the number of magnetic field lines passing through the loop constant. Since the number of magnetic field lines passing through the loop is decreasing, there must be an induced magnetic field to oppose the decrease. So I'll represent that by these two dots. These two dots represent an induced magnetic field that is trying to support or increase the number of magnetic field lines crossing that cross-sectional area, since the magnetic flux is decreasing. Now, that might be better understood by looking at it like this. Let's say we're looking at the conducting loop from the side. Here is the magnetic field that the conducting loop is passing through. As the conducting loop is moving to the right, fewer and fewer magnetic field lines cross the plane of the conducting loop. Because fewer and fewer magnetic field lines cross the plane of the conducting loop, the change of magnetic flux wants to prevent that. It wants to create a magnetic force to try to keep the loop from leaving, to try to keep the loop from changing the magnetic flux. In order to keep the loop from leaving, a magnetic field is created that is going to be in the same direction as the magnetic field that is passing through the plane of the loop. Now, it's in the same direction because remember, when two magnetic field lines are parallel to each other, they exert an attractive force on each other. That attractive force will try to keep the conducting loop from leaving. And now that we know the direction of the induced magnetic field passing through the loop, we could use the right-hand rule to determine the direction of the induced current. So all we got to do is take our right hand, and here is the thumb of our right hand. Here are our fingers, and we're using the version of the right-hand rule in which we take the thumb of our right hand, put it in the direction of the magnetic field, take the fingers of our right hand and curl it, and the direction of the curl is the direction of the induced current. And in this case, we would see that the current would be counterclockwise if we were to view it from above. So that would be like this. counterclockwise induced current. So now we found all of the current directions for parts A, B, C, and D. In part A, there is no induced current because there is no change in magnetic flux. In part B, there is a clockwise induced current because the magnetic flux was increasing. So there is an induced magnetic field to try to cause the magnetic flux to stop increasing. In part C, there is also no change of magnetic flux because the number of magnetic field lines passing through the area of the loop remained constant. No change in magnetic flux, no change in magnetic field lines, no induced current. And in part D, the induced current was clockwise because that induced current creates an induced magnetic field that opposes the decrease of the change of magnetic flux, or rather opposes the decrease of the magnetic flux. So putting all of this together, we see that for parts A and C, there is no induced current. For parts B and D, the magnitude of the induced currents will be the same. And the reason why the magnitude of the induced currents will be the same is because the speed at which the conducting loop is entering and exiting the magnetic field is constant, or rather it's the same. Same speed entering, same speed as leaving, which means the rate of change of the magnetic flux is the same when it was entering and when it was leaving, which means the magnitude of the induced current is the same. However, the direction of the induced current for parts B and D were in opposite directions. For part B, where we had the loop entering the magnetic field, we had seen that the induced current was clockwise. While for part D, the induced current is counterclockwise. So let's go ahead and summarize that. Induced current was clockwise for part B. For part D, the induced current is counterclockwise. And that was in order to prevent the magnetic flux from changing in each of those scenarios.